Hello my friends, my name is Shekhar and today I'm gonna do a video on how to use on-chip analog comparator of ATMEGA-8 microcontroller. So as you can see, this is the datasheet of my ATMEGA-8L microcontroller, ATMEGA-8L and ATMEGA-8A or 88. Basically same. These microcontrollers are basically same. So you can go through this. This is the most common or if you want to start by your own, then go through this text. There is a on-chip analog comparator on ATMEGA-8 and there is an analog input 0 and analog input 1. So whenever the value of analog input 0 goes higher than the value of analog input 1, a bit called ACO, this bit ACO is set. So in this block diagram you can see that there is one block for analog input 0, analog input 1, then there is an on-chip comparator. There is one more bit called ACD bit through which you can analog comparator disable. So if you are going into power down mode or you want to disable your analog comparator, and then by using this bit you can disable your analog comparator. So you can also select band gap reference, which will be then you don't have to apply any voltage at your analog input 0. It will select the internal band gap for you, and then with the help of ADC multiplexer output and ACME and ADEN, you can apply any of the ADC channels input to your to the negative pin of your ADC, and with the help of the output of the ADC you can trigger some interrupts also. So these 3 bits are responsible for interrupt select, and you can also select it on which case the interrupt should be triggered, like it should trigger on the toggling of this bit or in the falling edge or in the rising edge. You can also do that, and you can see that there is ACO. Whenever this A in 0 goes higher than A in 1, then this ACO bit is set. So this is all you have to understand to use analog comparator. Now there is a register called SFIOR, which is special function IO register. You don't have to use that, but just go through it, because if you are using ADC multiplexers output or the band gap reference, then these registers will help you. The register I am concerned about, I'll be using this ACO bit. So the register I am concerned about is ACSR. ACSR is an analog comparator control and status register, and I'm also concerned about it ACO. As you can see that initial value is not available for this register, and it is only read possible. You cannot write in ACO. So, and this is analog comparator disable, with the help of which you can obviously disable your analog comparator if you are going into power down mode. You can save the power consumption. And here is the bit for which I am concerned. The output of the analog comparator is synchronized and then directly connected to the ACO. The synchronization introduces a delay of 1 to 2 clock cycles. So there will be a delay of 1 to 2 clock cycles, but if you are running at higher clock, then I think 1 to 2 clock cycles won't bother you. So now coming to my code, the code is very simple. First I am defining what is the FCPU, then the normal some header files. I am making my pin C5 as an output, because I am gonna connect an LED which will show me that whether this ACO is set or not. And then there is a simple code, like if ACSR and one left shift ACO, this condition is stating that whenever ACO bit is set, this whole condition will be set. Right? It's like you can figure it out, just use some simple shift operators and using some simple shift operators and bitwise AND operator. So the point of using this is like whenever this ACO bit is set, this whole thing will be set. Or you can also do, I think it's read only, so you can do this. Sorry about that. ACO equals to 1. You can also do that, but I prefer to use this. And then whenever this comparator analog comparator output is set, I will set my port. I will glow the LED connected at pin C5, and then there will be a delay of 250 or something. And then and if the bit is not set, like in else case, I will switch off my LED. So to show you the demo, you can see that this one is connected to my A in 1 and this one is A in 0. So whenever the value of A in 0 will go higher than the A in 1, right? This is stated in their data sheet, like the input value is on the, and when the voltage on the positive pin is higher than the, so whenever the voltage applied at this A in 0 will go higher than the voltage applied at A in 1, this LED should glow. So as you can see that right now, this potentiometer is set at 50% and this is at 35%. So logically my LED should be off. So let's hope. And you can see I started the simulation and my my LED is off. Now what I'll do, I'll start increasing the value of my potentiometer. You can see that I'll start increasing the potential applied at this pin, the analog input 0, and after crossing 50 my LED should glow. So let's see what happens. Right now I'm at 42, 43, 45, 48, 49. So whenever I was at 50, you can see that this LED, whenever these two are equal to each other, LED flashed for a second or for a quarter second because of that 250 millisecond delay, and then LED is turned off. So whenever these two are equal, there will be some this bit is set for a moment or something. But whenever it goes higher than this analog input 1, this LED will turn on. So this is how you can use on-chip analog comparator of your ATMEGA-8. So let's say that you are using IR sensor and you want to you are using some simple single IR sensor. So instead of using transistor circuit or instead of using external analog comparator, you can use your on-chip analog comparator, and with the help of this analog comparator you can trigger external events, you can trigger the interrupts. So this can be helpful in designing applications like the one I am working on is, it's like whenever there will be a U-turn and whenever someone passes through that U-turn, the LCD will display some messages and the LEDs will start blinking. So you can if you are using single IR sensor, then this option is great. If you are using multiple IR sensors, you can also use multiple IR sensors, but then you have to use these ADC pins, and then you will be using this ADC multiplexer output. So now this analog input 1 will be from these, instead of coming from this block, analog input 1 value will be coming from this ADC multiplexers. So I hope you enjoyed the video, and thanks for watching.